Okay, so in this video today we are discussing fluctuations in an ideal gas using grand canonical ensemble. In particular, we are interested in the fluctuations in the number of particles. So we know that for an ideal gas we can calculate the grand canonical partition function exactly, and this is this calculation. So it's an exponential of exp of beta mu. Mu is the chemical potential, v the volume, and lambda t to the third thermal wave length. So now we calculate two quantities. We calculate the average number of particles, and this is the derivative of the log of the grand canonical partition function with respect to the chemical potential divided by beta, and this is the result, exp beta mu v divided by lambda t to the third, and we also calculate the variance using well-known formulas. The result is the same. So what does the result give us? So if I calculate the relative fluctuation, which means the standard deviation divided by the average number of particles, I get 1 over the square root of average n. And this is a quantity that goes to 0 in the thermodynamic limit when n becomes very, very large. So it means that this result tells us that the probability distribution of finding n particle, which is the nth term of our partition function, okay, it's strongly peaked around the characteristic average number of particles, right? And the standard deviation around it's becoming in this scale, n divided by n average is becoming very, very small. It's peaked like a delta function, which means that in the grand canonical ensemble, I can let the number of particles fluctuate, but basically the number of particles in the thermodynamic limits has very small fluctuations around the average value. We can repeat this analysis in a different manner, namely approximated manner. So we have an infinite sum over all the number of particles, and we are looking for the most likely n values of n, which is given by the maximum of the function that I define f of n, right? For convenience, I use the exponential. It's easier to minimize this function. So now we do the calculation. We find the maximum for f of n, and this will be the most likely value of n. So in the last line, I write this f of n is n times the log of exp beta mu v divided lambda t to the third minus log n factorial. Okay, and I use a Stirling approximation to approximate the n factorial in the usual way. We are interested in n very large. So these are the first and the second derivative of the function f, small f of n. Okay. Second derivative is negative, is minus 1 over n. So it shows that, well, now I set the first derivative to 0 to find the maximum. Now, we obtain the maximum by setting the first derivative equal to 0, and the maximum is n star, easy to compute, is exponential of beta mu v divided by lambda t to the third. But this is precisely the average number of particles that we have computed in the previous calculation. That wasn't the exact calculation, right? Therefore, now we can write the Taylor expansion for f of n by calculating first the constant value, which is f calculated in n star. But if you do the computation, you find that this maximum value, this f of n star, is precisely n star. And the next order is, due to the fact that the first derivative is 0, the next order is a quadratic n minus n star squared with a coefficient which is minus 1/2 n star. Okay, now we have put all this result of this analysis back in the calculation of the grand canonical partition function. Okay, so we have the exponential of n star, so we approximate f of n, so the final result is encircled in red. Okay, so where you have this red square, so rectangle, you see x of n star, which comes out of the exponential, right? And the sum over the other term. So I replace for f of n the Taylor expansion, okay? Remember, n star is x beta mu v divided by lambda t to the third. So the next step for us is to approximate this sum, discrete sum with a continuous integral, and that will give us a Gaussian integral. Gaussian integral is easy, it can be done. And this is done here. It gives an additional contribution, the square root. And plus I've added dots at the end because this is an expansion, and so therefore there are higher other corrections entering in there. So we note that what we are summing over, what we are integrating over, it's a Gaussian distribution, and the variance of this Gaussian distribution is n star. N star, we already know that is the average n that we have seen in the, just in the previous discussion. So finally, when we take the log of this grand canonical partition function, we find that the first term is exactly identical to what we get from the exact calculation. Okay, and this is an extensive term. It's proportional to v, the volume, as the system goes to the thermodynamic limit, n going to infinity, v going to infinity, and so on. This is the leading term, and this is the only term that we typically use in our calculations. Plus, there are higher order corrections, but these are of the order of log of v, and this is much smaller compared to the leading one.